Right, okay, so this week we're going to cover symmetric key encryption. So I'm going to call them symmetric key and asymmetric key. That's the proper way to define it, but you also might see it identified as secret key encryption. When we come on to asymmetric encryption, you'll see that we have two keys, a public key and a private key. So the focus of what we're going to look at is to do some of the basics around symmetric key, why it exists, how it all fits in together. So I'll show you the overview that I showed you last week and the complicated infrastructure of how all this crypto fits together, and then hopefully each week we'll fill in another little bit of the jigsaw, and hopefully at the end of the module you'll understand how this whole thing fits together and makes sense. Then we'll look at block and stream encryption. So you may think that the world is block encryption and AES is the only show in town. Well, it isn't. So the biggest rise on the internet, we'll see IoT devices, we'll see tiny little sensors integrating into the internet. These devices can't cope with complicated block ciphers, and as you'll see, they can be fairly power hungry. So we need to create ciphers which are efficient in battery drain, also memory space, and so on. So the new stream ciphers are coming along. And a very good chance if you connect to GitHub or OpenSSL, it's actually ChaCha20 that you're using, and it is in AES. And anyway, if AES gets cracked, we need to have a fallback there to very quickly swap over. So we'll look at the block and the stream ciphers and understand what they really mean and what's important about them. Then some of the methods, so 2-fish, blowfish, DES, 3DES, stacks and stacks of symmetric key encryption methods. We need to understand why they might be used. If there's legacy systems, how can we still use the code that's in there? So OpenSSL is the place that we typically go to be able to run our ciphers. And in the lab today, it's OpenSSL, it's Python again, and it's Node.js. So the three things are the core of what we'll look at and have all these ciphers built into it. Then we'll look at some basic salting. You might call it an initialization vector. It's something to make sure that the ciphers that you create are forever changing. Fortunately, the salt has to be stored alongside the cipher, so for hackers, it's not, it can be, it doesn't need to be a big task if you know the key to take salt from the cipher and then decrypt it. Then after that, we'll look in a bit more detail at what AES, DES, and ChaCha20 and RC4 I've actually got underneath from there. And then you might think you've got trillions and trillions of keys, but you put a password to generate, use a password to generate your keys, and you've just reduced the key space down massively. So key entropy measures how strong your key is. Anything less than 72 bits, key entropy is crackable with an NVIDIA card. Next week we'll look in more detail at Hashcat and how Hashcat can use the NVIDIA cards using the CUDA architecture, and you'll see that the computing power is there to be able to crack encryption if we have weak methods that we've used. So here we are. So last week we did some fundamentals. This week we'll do some symmetric key, hash next, public key exchange, and then on to there. So our first assessment happens in week 9, and it'll happen on Friday, and it's a test taken on Moodle. So I'll get you set up for what's going to be asked. Each week, if you go to the website, you'll find there's lots of little questions that you can actually do that are up to MSc level. So that's where we are, and that's where we're actually going. So this is the roadmap of what actually looking at. And this is the symmetric key here. And symmetric key is used to protect data at rest on a disk, on air, over the network. So symmetric key that's actually doing the protection of the device, of the data. And we need to make sure that Bob and Alice, if they're exchanging data, have the same key, and that every single time that they connect, a new key is created. So we have our key exchange fitting in there. So we need to generate a key which will be set up for the next part, which is to do our symmetric encryption. So 128 bits, 256 bits are typical key sizes that we would use in there. So the hashing is there to make sure it's all trustworthy. Some integrity, the certificates are in there to make sure that Bob and Alice can be authenticated to each other as part of the key exchange. They know that they're actually dealing with the right entity and that someone hasn't jumped in between and changed the other side. And then we need a public key to be able to prove the identities and to sign data. And then we've got all this other stuff to do our basic privacy. So that's the infrastructure that we have. So let's look at some of the basics. So some of the basics are that we've got Bob and Alice, and unfortunately we've got Eve there. So what we really need is to make sure that we have privacy, we have identity, and we also have integrity. So you can call it CIA, AAA, or whatever. But we need to create systems that are secure, authenticated, and can be verified. So we often have to bring in Trent. So there's my coffee cup I got just a wee while ago with Trent, the trusted one. So Trent's in there to make sure that Bob can authenticate or prove his identity to Alice, and vice versa. And we'll find later on in the module, John Napier provides a core part of that whole authentication infrastructure. So what we have is a standard encryption method that is well published and is known by all. So we don't keep anything secret because it doesn't do any good to keep it secret. We use a well published algorithm. The last thing that you do is cook your own crypto. There are many cases of companies creating their own encryption methods and their own hashing methods and so on, and they've become unstuck because there are weaknesses. So we use standard methods that are well published, that have been peer reviewed and evaluated. Do you know the standards agency which will typically approve any encryption method? Unfortunately, this website seems to be off-site. Who is it? NIST. So NIST have competitions every now and then. They get a bit worried about something and they have a competition. So they had a competition around AES, deciding that DES and 3DES were not fit for purpose. So the method that won was, do you know what it was originally called? Rendal. So Rendal was named after the two Belgian cryptographers that created it, who then went on to do SHA-3. But then the competition, famous people submitted their own encryption, and it was AES that just wiped away all the other competition. Another one that happened was for SHA-3, a hashing method. And this time, it was all about IoT devices not being able to cope with some of the hashing methods that were around. We'll find SHA-1 and SHA-2 and so on. So there was a competition around looking for a new hashing method. SHA-3, you'll find, where would you find SHA-3? I think, where is it? Where is it? best known just now. That's in Ethereum. So the hashing method used in the blockchain is often SHA-3. So we have a competition, we define a standard algorithm, and now what we have is that we have keys. So the key needs to be generated, and we've got to watch that Eve doesn't listen to the communication so that she can find out the key. So in there we use a key exchange method to make sure that we can talk openly, and at the end of it, Bob and Alice will have the same key. So as we'll see, we use Diffie-Hellman, elliptic curve Diffie-Hellman, for that to happen. Every time you use SSH, every time you connect to the HTTPS, it's a key exchange that goes on. What you've got to worry about, though, is if you have a long-term hack of a key, it could release all of your information. So that's the basic infrastructure that we have. So we have our public key methods, our hashing methods, our encoding methods. In this lecture we'll look at our symmetric key encryption, actually 2, 4 DES, 3 DES, and AES. As we looked at last week, the number of bits that we have in our key increases the number of keys that are possible. So if we have to brute force, then we need to understand how many keys that we can actually use. We're now talking about tera keys per second. So as 1,000 billion keys could be tried in a single second. For what cost? For a fraction of a cent. So it costs you about $10 an hour on the Amazon cloud to hire 4 GPUs. Each of those GPUs has 4,000 cores. So we need to understand where we are. And the limits are basically there. So if you turned every computer on in the world and then gave them all a few keys to try, through brute force, 72 bits is achievable within days. It's going to cost you a lot of money to do that, and you're only going to crack one cipher, but that's the limit. When quantum computers come along, then that is going to jump quite a bit. So in 5, 10 years, quantum computers will run much, much faster than existing systems. And they'll get near to 128 bits, but it's still okay. So, the lesson is that you should go for 256. If you're really worried about quantum computers coming along, cracking, then just go for 256. If it's not a performance issue, then you'd be as well to encrypt with 256. But symmetric key won't be too much okay in terms of quantum computers, because there isn't fundamentally anything wrong with the method that it uses. In public encryption, because of waves, you can actually crack both elliptic curve and discrete logarithms. So that's where we are just now, and we need to understand the number of keys that we have. So if we take an example here, so there's a 64-bit key that we've got. That's 18.4 million different keys. It's going to take you a long time to crack that. So even if you're cracking at tera hashes, it's still going to take a long time to do that. So if we do the calculation, and we take a 1 gig clock, so it's cracking 1 billion a second, then it takes about 2.5 million hours to go through the full key space. 285 years to do that. On average, it'll be half of that. So it's still over 150 years. But every year, computers get more powerful. So then after the first year, it only takes you 143 years to crack it. And then if we keep going down, actually, after 9 years, it only takes a year. And then after 17 years, it takes 20 hours. So because of things like Moore's law. Then it says that computing power doubles every, how often?
Yeah.
It's about 18 months or so. We've kind of short-circuited that to the sense that we've almost got to the limit of silicon speeding things up. So the only way we can speed things up is to run the pan and so on. But almost every year we lose a bit. A bit falls off the end, and it gets half as difficult. And because cloud is the one product in the world that gets cheaper every year, it gets cheaper to crack. You don't have to buy an NVIDIA card anymore. You can just go to Amazon and get rented time. You can buy time on the stock market. Amazon has ways that you can buy some time. If there's free time, you can put in a bid for it. So you can do things quite cheaply from there. Just let me stop that. From there, what's happened? If you look at something like DES was 56 bits at the time. It was developed in 1975, and 56 bits is easily crackable within almost seconds on a standard desktop. So you shouldn't go anywhere near the limits of the 72. And then what we can do is we can run in parallel, because it's a highly scalable method. Half the keys go over here, and half the keys go to that one. Then we can go for 16 and so on. And we can start to run massively parallel systems where we can give each one part of the key space, and one of them will hopefully find it and tell the other ones, and then that will be it cracked. So if we now look at adding number of processors and improvements in technology, then our long time actually is crackable in just a short time if we manage to build an array with 1 million processors and just increase the computing power. It doesn't take much to do. So we need to make sure that what we create, if we don't use the full key space, that we aren't giving an intruder an opportunity to crack our perfect ciphers. So there's one guy there. We'll look more at them next week. But this has got 3,500 CUDA cores in it. Hashcat, refined, just loves an NVIDIA card. We have got a server that we'll put online soon, but these devices have over 4,000 typically, 4,000 cores, and they're optimized to do crypto. They like doing hashing and crypto methods. It's all done in hardware. And the power that you get from them, so that's the kind of things that you see in a hash, a mining factory. So this is just racks and racks and racks of GPUs. So if you go around some of these data centers, you'll find the consumed masses of energy. This is the cooling system, just to cool these things down. And all these factories are doing is trying to find a hash for the kind of block. If you do that, they get paid 12.5 bitcoins. Once the market isn't there for bitcoins, if it halves again, then you'll see all these factories and GPU cards getting dumped and so on. But that's the kind of cracking that you can get, and obviously you can do that more in the cloud, as we'll see next week. So there's an NVIDIA GX 970. Does anybody have a good NVIDIA card for the machine?
Yeah, more or less the same.
That one?
970.
Yeah. So it takes you about a year to make money back, but you've got to keep it on all the time. So if you wanted to do Bitcoin mining or Ethereum mining, then that guy, or what NVIDIA say it's going to take you about a year and you'll get your money back. So you win. Sometimes you can be part of a mining pool. So Monero creates a mining pool. Unfortunately, when you went to Starbucks, at one time there was a little JavaScript that started to mine on the machine. They forgot to stop to throttle it, so your CPU went up to 100% from that. So this card here is doing 182,000 gigahashes. That's a billion. So it's nearly a trillion hashes per second for that. So that's the kind of device that you could be looking at from there. It says you get $500 a year that you're doing your mining. Okay, so that's our keys, and we'll look in more detail next week at that. So the way that we do our ciphers is we either do it by stream or by block. So by block, what we do is that we take a block at a time and then we cipher it. We then stitch together all the cipher blocks and we send that as a cipher stream. So typical size of a message block is 128 bits. How many bytes is that? So if 128 bits, how many bytes, how many characters do we have in there? 128 bits, how many bytes? Anyone?
16?
16? Yeah, so you have 16 bytes at a time, or 16 characters. You can basically tell the length of your ciphertext roughly by the number of blocks that are actually created, because they'll be created in these 16 blocks. So you can see exactly, almost, how many characters your message has got. So each block then is ciphered with a secret key. And as you see, there's also what's called an initialization vector, or some salt gets added to it, and then we create our cipher stream here. The other method that we use is a stream cipher. With a stream cipher, we use a secret key, or a seed. We also need an initialization vector, or some salt. It then goes into some little algorithm and produces a pseudo infinitely long key. So the key will go on forever and ever. It's called a key stream. And then all we need is a little XOR gate. If you've ever seen the electronics, looks like that. So that's the complexity of our circuit to create our cipher stream. And the good thing with this is that this gives us real-time cipher. So every bit that we receive, we can decode on the other side by just taking the same cipher stream and XORing it again, and we come back with the same plain text. Unfortunately, this was part of WEP. So if anybody remembers WEP a long time ago, it was a complete disaster. And the reason it was a disaster was that the key size itself was only 56 bits. So it was 64 bits, but 8 bits were parity bits. And as you've seen, 56 bits is easily crackable. The other thing is that this random seed was too short, which meant that after a certain amount of time, it rolled over. It's 24 bits. It rolled over in a few hours sometimes. And once it rolled over, you basically just remembered what was sent with the same IV value, you XOR it together, and magically the stream was cracked. So it gave stream ciphers a bad name, and it really wasn't the fault of the RC4 algorithm that was used. It was the fault of the designers of Wi-Fi originally. So now, when you connect, it's AES. AES that you use virtually all the time, because this type of cipher really isn't fit for it. But it was created in a time that had very simple network cards and couldn't do the complexity of AES encryption. So there's RC4, basically your key, your seed, and your initialization vector, your salt, going together. There's a few lines of code. It creates a scrambling thing, and then we get a long key stream created. As long as Bob and Alice can create the same key stream, then they're able to decode it. So there it's there, there's the data stream. We take a 1 and a 0 in XOR, and we get a 1. We take a 1 here and a 1 there, and we get 0 there. So in real time, we can actually get the data. The other great thing with this is that we can splice the data stream up and run it in parallel. So if we want, we can actually run through, we can chop up the data streams, chop up the key, and run each of these in parallel with threads, and we can multiply up. So this type of stream can give us gigabits per second, but a block cipher really struggles to get to that level. So what happens in our block cipher when we get to the end and we don't quite fill all of the blocks? So let's say we have 27 characters. I'm going to encrypt them. So we fill the first one up with 16, and now we've got 11 there, and we don't quite fill the last part of the block. With that, we've got to pad something in there, and then we've got to strip that off at the end. So we use padding to do that. So the main methods that we use are these ones. The most commonly used one is this one. If you ever decrypt a cipher and you've got strange characters at the end, it's usually that the padding is incorrect when you're trying to decrypt. With this one, what we do is that we count the number of bytes that are missing, and we put a hex character equal to those bytes in a consecutive way to fill up that last block. So there it's there. So there's 1 character, 2, 3, 4, 5. So you can see we've got 5 characters in there. Those are the ASCII characters there. And now we're missing 11 characters to take us to the end. So the padding becomes 0B, which is 11. If I add on another character, what will I pad with? 08, and so on. So if I give you a little demo of that from there. So let's look at encryption and then go for padding there. It's going to bring up. Okay. Okay, so we can see here, there's my ASCII stream for hello, and I'm padding, I need 11 spaces. So if I now go to there, we should now see that we've got 7. So we'll get to the end. So 7, 8, 9. So try that. Okay, so now there's 3. Go again. 2. And now we're at 1. So what do you think will happen next if I add another character? What was it? No padding, and what will happen? I'm going to have to jump to another block. So you should now see that the block size will double, because we've opened up another block, and now it's got 1 0. 1 0 is what in hex? 16. Okay, so we're padding with 16, so the whole block is almost like a padding block in there. So we don't have to use that method. There are other ones that we can use. We can pad with zeros and so on. But CMS is the standard. It's the one that's used in certificates and in key definitions and so on. So that gives us our cipher padding. So what are some of the methods that we can actually use? Well, one of the first, and it's still pretty much uncracked, is DES. So DES, I think, was created in the 1950s and was a standard 56-bit key. So it was secure at the time, but unfortunately computing power is caught up with it. Bruce Schneier created his methods, true fish, low fish, and so on. And then we see Ron Rivest cipher, RC2 and so on. But Rendell is the one that's used most often these days. Okay, so there are various ways, and we've got demos of these online. I'll explain how 3DES works later on in the lecture, but many systems still used DES, and they had to find a way to create compatibility, so we created 3DES. Okay, so that's our methods that we have. So now the problem that we have is that if Eve captures Bob's ciphertext, what's to stop Bob from replaying that back to Alice? What's to stop Alice copying and pasting ciphertext together and making it look like a valid message? So Eve doesn't have to decrypt the message. She can basically go ahead and copy and paste the ciphertext together. So the solution to this, and we'll see this again with hashing, is to add salt into the cipher process. So with this, if we take the standard ciphering, then we take a block and we encrypt each block. And if we have the message hello in each block, then it will end up being the same cipher in every block that we have. So to overcome this, we add salt to our initialization vector to make sure that the first block will always change depending upon the initialization vector. Then what we do is that we often take the output from one block and then feed it into the next one. In this way, we chain our ciphers, and they're all dependent upon this initialization vector. So this shows an example here. So there's our original image. This is the image using AES with ECB. So ECB just takes each block and ciphers it. And you can see here, we can still see the penguin. So why do you think we can still see the penguin in there, although we're using AES encryption?
Because the same colors have the same code.
Yeah. So the same, we take blocks at a time, so the same blocks that have the same colors will be ciphered in the same way. If we use CBC here, we can see that what we get is complete noise. So an encryption method is measured on whether it looks like noise or not. It's the standard way that you can detect if somebody's using encryption, is that you measure the bytes, and if it just looks completely random, then it's likely that they're either encrypting or doing something else. What's the other thing that they might be doing? So apart from encryption, what also looks like random numbers? Was it?
Hashing?
Hashing,
Obfuscation.
nearly obfuscation. Well, it would be compression. So compression also does that. It creates something that looks almost random. But this here should be completely random. And we measure what's called entropy of the file, and it will tell us if something is encrypted or not. So here's an example here with DES. So if I take this as my input, all E's, because DES uses a 64-bit block size, and this is my blocks that I have. So each block is then encrypted as a cipher stream of this, if I use this key. So then each one is then has the same output. You can see here from the cipher stream that we repeat here, and we repeat again here. So in this way, we can actually see the same output appearing. So one of the most important methods is the AES method. So AES uses a concept called an S-box. So an S-box takes our bytes that we produce and puts it into a table here. So it's a bit difficult to see, but if I have a value of 5, 4, then the output becomes this value here. So in this way, our cipher stream is scrambled. So it's a bit difficult to see, but we go through 10 rounds of this manipulation. When we encrypt, and then on the other side, when we decrypt, we basically do the reverse. So the first thing here is the S-box. We take our 16 bytes and we put them into an array of 4 by 4. We then put these bytes through our S-box and we get our output here. After that, we then scramble the rows. This is a row scramble. And then we scramble the columns. And we go through that for 128 bits 10 times. And that's the basic operation that we do with AES. Unfortunately, as we've shown here, that leaves a footprint. So in our research here, we monitor the electrical supply to a device. And the operations that goes through there leaves little spikes as the processor is doing things. So it's not too difficult to actually reverse engineer the encryption key because you know the S-box. So this is the S-box for encryption, and if you do the reverse, you'll find if you go from 20 here, there's us back to an original value that we had. So this one does the inverse of what that one does there. So up to now, it's been uncracked, but somebody could come along and find a magic way to reverse this from here. Unfortunately though, your key is sitting in memory. A lot of developers don't protect their key, so they just put the key into memory, and then if the memory is made readable or is dumped, then the key is extracted. You then look for the most random values in your memory, and you'll find the key sitting there. So although this method looks perfect, there are many ways that we can use to crack it. Israeli researchers looked at the electromagnetic waves that were giving off by a device, and even the sound as it goes through the encryption process can leak keys. So the way that DES works is that we have a key of 56 bits. And what we do is that we encrypt with a first key, we then decrypt with the second key, and then we re-encrypt with the first key again. Why do you think we did it this way? Because it looks inefficient. So this gives us an equivalent of 112 bits. So why do you think we created such a complex system as this? If I replace that for key 1, could you tell me what happens there? If my key 2 is just key 1, I go through these steps.
It will be plain text.
Was it?
It will be a plain text.
No, that should still be encrypted. If I take key 1, encrypt with it, and then I decrypt with it, and then I re-encrypt with it, what's that equivalent to? Was it?
You're just doing it once.
Just do it once, yeah. So to keep compatibility, basically, all they're doing is that becomes DES. So the reason they did 3 DES was that they could still keep compatibility. If you had a Cisco device, say, which is in a tunnel, and you're still using VPN DES with VPN, then you could still use the same chip. You just have to feed the same key in at 3 stages from there. So in this way, we can keep compatibility. So the next method that we're looking at is Cha-Cha 20 and RC4. So these are stream ciphers. Cha-Cha 20 was created by Google. So its main purpose was to make sure there was an alternative to AES, but also to have a cipher that allowed us to be able to run on IoT embedded devices. So the standard is there. So this one here does what's called a MAC. So you can sign a hash with a symmetric key. That's for the signing process. But the basic cipher itself is Cha-Cha 20. And you'll find it in lots of places. So there's a chance that when you're connecting to, say, Google, most browsers now support it, but it's integrated into TLS. So you might think you're using AES, but under the hood, you're actually using Cha-Cha 20 as a stream cipher. So if we try the cipher itself, hopefully we'll get an example here. That's just my little JavaScript implementation. So there you go. So our input is this. I create a key seed based on a passphrase. So we'll see that next week. But I just take the hash of the words of the passphrase here, and I create my key stream. You need to remember that this is a randomized. This is a randomized key. Anyone who goes through a dictionary, and if the word QWERTY is there, they will generate the same key as me here. So this is a key stream that we've got. Our text stream, we basically XOR the two together, and we end up with our output stream. So what information can you find out for the length of the cipher stream in Cha-Cha? What does it give away? Just by looking at the cipher stream, what can you see from it? Was it? Wasn't it? Okay, so the stream cipher, the amount of bytes that you have going in, what we call the amount of bytes that you have coming out from there. Okay, so in that way we can we create our cipher stream. The other method that's fairly common in cipher streams is RC4. And this is the code here. So this is our S box that we saw before. So this creates a little S box for us, and then this creates the little code for working on the S box. So this is how we create our key stream. But look here. Look here. So this looks very strange. We're putting a little piece of code into an infinite loop. This is a bad thing to do because it's never going to stop. But Python is interesting because what happens is that with the yield statement, it stops. So it provides a block every time it's asked for it, and it will keep providing that block as we go through the cipher stream. So Python has the ability to use this yield method to stop and then wait to be asked again. So we can see the code running here. Okay, so that's me generating the S box for this this key that I've used. And if I use the same key, use different keys, then we'll get a different S box. And then we get a key stream that looks like that. So if we only want 56 bits, then this will be the key stream that we actually get. And the code itself will do that because of this yield. And when we run the code, so that's all our little encoder is. It's an exclusive OR operation. We take 1 byte at a time, and then we take the output from our key stream. And then each time that we go through our characters, we do that yield again, and it'll produce back the data that we actually need. Okay, so that's our setup that we have for that. Make a little start on the next part. So we went through basics, block and stream. So hopefully you're starting to pick up a picture. You'll find it can take a while for everything to settle in, and we'll do some practical work today, and hopefully some of the things that we went over will become more in place once you do the practical things. And then once we get to the test, hopefully you'll understand how it all works together. Salting process is so important. You'll find every single time that we cipher, we'll get a new cipher stream, even though we're using the same key and the same plain text. We'll get a different cipher stream. But as I said, the salt, the initialization vector, is stored in the cipher stream, so it's not too difficult for an intruder to actually take your salt and try out lots of different passwords and end up with the same, discovering the key. And we'll do that in the lab today. Basically all you do is that you just keep trying keys and you get an exception, sudden you don't get an exception and you've cracked the key. So encryption gives away the key and when the keys aren't successful because it will create an exception whenever you try. So these these crypto crackers will often do that. They'll keep trying keys until they don't get an exception. So the concept of key entropy, I can't highlight how important this is. So we're going from 128 bits. I don't know if you've seen 128 bits. That's a very large value. So if we try our little Python code, oops. How many keys do you think? Just give me a rough idea. 2 to the power 128. Anybody want to take a quick guess? I'm not asking for an exact value, but is it millions or trillions? Or what do you think? That's that number. So that's 1,000, 1,000,000, 1 billion, trillion. Lose it after here. There you go. That's the number of keys that are possible in 128. No two people who create the same 128-bit number is ever likely to have the same one again. So if it's completely random, you're safe. If it's 256-bit, that's the number of keys that you have. In the whole history of our existence on this planet, if everybody generated a key every single minute of the day to the end of the time of this planet, they will never generate the same keys ever again. So if you can, you make sure your keys are completely random. And if they're random, it's impossible for somebody to discover your keys because there are just too many keys to work through. Unfortunately, we're humans and we often generate our keys from passphrases or passwords. And the strength of our keys that we're generating is basically based on the total amount of keys that we can actually create. So typically what we do is we'll take a word, a password, and then we'll hash it. So we'll go over hashes next week. But we take a hash of it, and then we use that as the key. So it's not too difficult for somebody to do the same process as us. So if we take 0 to 9, and if we create an 8-character PIN code, then the total number of passwords that we'll have is this number here. To work out the key entropy, we take that value, we take it to the log 10, and divide by the log 2, and we get some idea of the equivalent key length that we would have. So we can see that 26 bits is far too low. So it wouldn't cost us much to be able to crack a 10 and 8 digit passphrase with purely numbers. So as we keep going from A to Z, we can have 26 characters. And the total number of characters that we're going to have is 26 to the power of 8 if we're using 8-character passwords. So again, if we try the entropy, we're up at 37. 37 is easily crackable on your desktop machine within possibly seconds. We'll see in a little minute. And then if we use upper and lower case, we add on another 7 odd bits in the key strength. So it's double is the increase in key strengths just by changing from upper and lower case. But as we found out last week, we all just use one character. I think at least half of us only use one uppercase. So we've already reduced down the key space because our cracking system just has to put the uppercase at the start. And what do we do with the numbers? Again, last week we found that virtually everyone here puts the number at the end. So hashcat and so on, and key cracking doesn't have to go through the full space, just basically looks at the most common ones, looks at the most common words, makes the first letter uppercase, and adds a number onto the end. I think there's only 2 or 3 people who put the number in the middle, as I remember. So if we go for A to Z, upper and lower case, 0 to 9, we're only at 47 bits. And if we do any of those characters, 48 bits. 48 bits is easily crackable. So let's try that. So we'll go for a fairly good cracker. So let's go for a tera keys per second. So this is a cracker that will do a tera keys in a second. And we'll only give it 1 core, that's fine. So let's go for A to Z. So how long do you think an 8-character password or a 8-character word that gets converted into a key, how long? Go and take a guess. 8 characters, A to Z. Seconds, minutes? Minutes? Do you want to put money on it? No. 8 characters, A to Z, 0.2 seconds. That's the maximum time. The average time is 0.1 second. It takes a tera cracker 1/10 of a second to go through every single permutation of A to Z. For 10 characters, 2.3 minutes. 2.3 minutes. So if you put all lowercase and you use 8 characters, 2 minutes, and it's discovered. Okay, so let's go for A to Z. So you've now been asked upper and lowercase. What do you think now? 8 characters, upper, lowercase. What's a kind of estimate? How much more difficult? 20 seconds for the whole space. 53 seconds. So 25 seconds on average to crack every single upper and lowercase value. For 10 characters now, a day and a bit. Will take you up to 10. So 10's finished in terms of just upper and lower case. We'll now add numbers onto it, and for 8 characters, every single A to Z, upper lower case, and numbers in the middle at the end, wherever you want, they all get cracked in 3.6 minutes. And then we get asked,
So tera is like 10 to 12 or
is
something?
yeah.
How much would it cost then?
So I'll show you next week. A tera on Amazon, it costs, I think it's $8
If
an hour.
add this on like when you're making a password, add this, like it would take, just so you know, it would take this amount of time to crack your password.
So there is systems online and they're terrible. So I put in QWERTY11 and it looks at a different type of entropy. It looks at the difference between a Q and a W and thinks that's entropy and it isn't. So if I put all Z's in, it shows a low entropy. If I show words that have letters that change, so don't trust the entropy checkers online because they just don't work well. So now if I add on that, so that's a password of tilde $5 A Z O 0 dot whatever, and let's see how long it takes. 15 minutes. So every single password that can be generated from upper and lower case digits and all those other characters will be cracked in 15 minutes. And here, well, we're not too bad now. We've up to 57 days, but that's the full space. It's enough to generate your whole rainbow table and everything. Remember, you have your salt, so the salt doesn't help you here. So you have your salt, you have your whole common words that you have, and then you put them together, keep going until you don't get an exception. If that doesn't work, what do you try? So rainbow tables don't work anymore. So rainbow tables are not successful because rainbow tables aren't built with salt, and few people don't use salt anymore. So it doesn't do any good to download the rainbow table and try it, because most of your hashes and your crypto will have a salt. So the first thing you try, take the salt off and try common pass phrases. If that doesn't work, what would you try next? It's what we're doing here. Well, this is brute force. So brute force is going from A, AA, AB, AC, and so on. And that's the way the hashcat works. It goes through these combinations. But we can target hashcat by saying don't bother doing upper and lowercase for the second letter and so on. Just concentrate on an upper and lowercase for the first letter, and only concentrate on 8 characters. So anybody with an 8-character password or key in the to generate the key will be targeted by it. And then you might target putting a 1 at the end, and then a 2, a numeric value at the end. So we'll find that hashcat decimates this type of calculation, and that this is showing you the worst case. If I have to go on Google now and you have used a completely random password, then these would be the times. But most people are using a password which is much, much simpler than that. So that's the example there. Okay, so that's the measure that we use, and we have entropy in there. Okay, so we've covered really the basics of symmetric key. Hopefully you're starting to understand why we use salt and the difference between our block and stream ciphers. So if you could get your phone out again this week, and we'll see how much you've learnt from what we've done. So just let me log in. Hopefully I can remember my login. And it's okay, so if you go to menti.com, yeah, if you can, yeah, that's okay. So if you go to menti.com and put in that code. That's it, got it. Good, 5 connections. Okay, mostly connected. Good, so it's 10, 85, 29. Good. Okay, so get yourself a name with 20 words in there. So we've got 26. Good. Okay, so you get more points for speed, but you don't get any points if you get it wrong. Are you ready? Okay, here we go. Right, so which is not a symmetric key method? RSA, AES, Blowfish, Cha-Cha 20, or RC4. 10 seconds. That's good. Oh dear. Well, at least you didn't go for AES, which is good. AES is a block cipher, Blowfish is a block cipher, Cha-Cha is a stream cipher, and RC4 is a stream cipher. Symmetric key RSA is not. RSA is a public key method. So we'll see how we got on. Hashberg. It's done okay. People's Vote did very well there. Disappointing burrito. Something to do with lunch there. And then Pingu's doing quite well in there. Jabot again doing well. Okay, so for the next one, let's see how we get on. Okay, what was AES originally known as? Ticklefish, Two Fish, Superfish, Blowfish, Raindal, or Rainmate. Yeah, good. I did mention it. It wasn't there. As a Raindal from the two Belgian creators of it. It was made Raindal and it became AES. So let's see who was listening. And this time it's Will B doing well in there. That's Jabot again. Jabot won last week, was it? Heshberg, Clementator, and it's good. Oops, let me do question 3, hopefully. Okay, for this one. Who created Cha-Cha 20? Microsoft, Intel, Cloudflare, Google, Facebook, or RSA? Yeah, good. You were listening to that one. It was Google who created, and they're flogging it like anything because they can, because they have 80% or so of the browser market, so they can push browsers to support their crypto. So let's see who got that one right. It's People's Vote doing well this time. And it looks like it's still Jabot. Jabot, who's Jabot? Right, well done. Hesper, did you win last week? You won last week, didn't you? I'm monopoly this, but it's quite close. Clementator was the fastest there. Okay, get ready. It'll get a bit more difficult, I think. Which is a stream cipher. Is AES, DES, 3DES, Blowfish, or RC4? Yep, it's RC4. I gave a wee demo of it as a stream. So it did well. Still, is it still Jabot? Clementator is just a wee bit faster there. Oh, who's Clementator? Very good. And who's Hashberg? Hashberg, good, excellent. So there's a kind of three-way split at the top there. Come on, hey ho. And the People's Vote, and not that I'm biased towards People's Vote at all here, and Mim and Jamie and so on. Jamie's used your real name there, Jamie? That's not you, it's another Jamie. Okay, start question 5. See how you get on this time. Okay, block cipher has a 128-bit block size. How many bytes will be processed at a time? I did say it. 128 bits. How many bytes are in 128 bits? 16. Well done. You were listening. You didn't answer me, but you were listening. That was good. 16, 16, 16. I'll say it a few times, okay? 16. And then you pad for the number in there. So that was good. 128. There's a bit difference between bits and bytes. You need to talk about that a bit more, but that's fine. Divide by 8. That's the standard way that you do it. So let's see who's doing there. Still Jabot. Oh, AO. It's doing well, and hey ho. think they get a bit more difficult here. If you've got 10 billion passwords to try, and you're going to crack with 1 million passwords a second, how long will it take you to crack all the passwords? Quickly. Just in case you get this as your millionaire question. I'm not expecting you to get this one right. Well done. Impressive. I'm not going to check that one. But yeah, that was 8 people got that right. So this should be quite interesting to see who got this one right. Whoa, there we go. Oh, Jabot. Yeah, you're struggling here. When the heat goes up a wee bit, yeah. Oh, Climatator. Who was Climatator again? Well done. That was. How did you get that one? Did you just guess answer C? That's good. And we've got Min in there. It's good to see Min. Will be and so on. People's vote was the fastest actually. Whose people's vote? Your people's vote. Okay. You trying to say something? Okay. So question 7. Oh, was that a question there? Did I miss a question? Okay, for brute force, if we go from all A's to all Z's, how many passwords do we try? Roughly, off the top of your heads. Estimate. If you get this one right, I'll be really impressed. And the answer is 17,000. 17,000. Who said 26? Who's the 3 people that said 26? I'll come and search you out, okay? It's not 26, okay? That's for sure. It's 26 times 26 times 26. 26 to the power of 3. How do you do that? I don't know. Just think up 20 times 20 times 20, something like that, and I think you'll get near that value. Okay, so the winner and the person who wins the T-shirt this week is. Well, people's vote did well there. Climatator's the one that's going to win, and it's by a long way, actually, by an awful long way, surprisingly long way. Okay, so we'll do practical stuff today in the lab. As I said, we're using OpenSSL. It should be installed in your Ubuntu instance. We're using Python because Python is taking over the world in this space. And we'll also use Node.js. So Node.js is a very important infrastructure. We've got time, we'll even use JavaScript at the front end. Okay, well thanks very much, and I'll see you for the lab at 3 o'clock. Okay, thank you.